Welcome back to another lesson about the art and science of computer technology. Today's lesson will be covering Python operators. Operator groups: arithmetic, plus, minus, times, division, modulus, exponentiation, floor division. So pretty much for these ones are all self-explanatory. This is multiplication, this one's division. It's going to return a float for that. Floor division is if you want to have an integer returned. Exponentiation is just raising something to some power. And modulus is just going to return the remainder. So for instance, if I divide 22 by 10, or here, 22 mod 10 would get me 2, because the remainder after dividing these fully would be 2 from 10 into 22. For the assignment operators, I think we might have gone over these earlier. They're pretty self-explanatory. This one's just regular assigning, and all the other ones, just think of it as x plus equal 1 is the exact same thing as x gets assigned x plus 1. So wherever you see this operator, you can just replace it with the subtraction or the multiplication or any of the other ones, and it's the exact same thing. For the bitwise, I put a little star next to this one because out of all of these, it looks like a pretty long list, but really the only one that's even remotely challenging for the most part is going to be the bitwise operators, because they're actually going to operate on binary kind of stuff, so ones and zeros. So these took a minute for me to get. I'll cover those. Each of these we're going to cover in a little bit more depth in just a second here. So, but for these, it's just bitwise and, or, XOR, not, left shift, right shift. And we'll go into detail with all those. Comparison: equal to, not equal to, greater than or equal to, and less than or less than or equal to. These ones are all simple math we learned already. Most of these are simple math we learned already. The ones that we don't know, for the bitwise operators, it's the exact same concept as what I just showed over here for the x gets x plus 1, whatever. It's just doing it with a different operator, but it's the exact same concept. This we all learned already. The only thing slightly off is the modulus and the floor division, but they're all using concepts that we already know, just using symbols that we haven't learned yet, possibly, depending on how new you are to programming. Anyways, so here we have the comparison operators, and for identity, is not. So we'll go into details with all these. Logical and or not, I believe we covered these earlier when we were doing the if conditions and all that. Membership, in, not in, so is the letter A and the word animals, stuff like that. You can do it with lists as well. So for instance, say you have a list of employees, you can say, is this person in this list? Or if you have a list of favorite movies, you can say, is this movie in list of fave movies? Stuff like that. Alright, moving on. Arithmetic, real quick. This is addition, subtraction, multiplication, division, always returns a float. Floor division, division returning an integer. Modulus returns the remainder after division, as we just showed with the 22 mod 10 example. And exponentiation, so it's just like 2 to the power of 2 would just be 4. Really simple stuff. Or if you wanted 2 to the power of 3, that would be 2 times 2, 4, what is that, like 8 or 16 or something? I don't know off the top of my head. Anyways, so we got that. Moving on to assignment. As we've just shown, x is equal to x, and plus and equal to is shorthand for x gets x plus y. So usually the first one is just whatever you're reassigning it to for what it started with, and then y is what you would actually be adding to the equation, so like a 90 or whatever. So there we go. And again, it's just pretty much just an equal sign after the operator right next to it. And yeah, real simple stuff. Bitwise, these ones, I'm not going to go super into detail with this because yeah, there's quite a few bit more to be able for me to do it off the top of my head. But anyways, as long as you get the basic concept, you should be able to figure out when you actually need to use it. You can like get a paper and pen and figure out exactly what your code needs. But bitwise operators are used to compare binary numbers. So bitwise and, bitwise or, bitwise XOR, and bitwise not. So here's a little table I made that just shows what the result would be for each of these. So let's say that the first number is always, so like over here, 0, 0, 0, that's going to be our first number. And then if we bitwise AND it with 10, 10, then the bottom number is what you're going to come up with, right? So this concept right here just applied in vertical format on the bottom. So 0, 0, 0, bitwise AND with these, you're going to get zeros because it's the exact same concept as the other logical operators we were talking about, where true and false will always produce a false, or true or false. It's the exact same concept, just a different symbol. But and or, it's the same thing, just you're applying it to ones and zeros on a bit level rather than applying it on a variable or whatever other value you happen to be evaluating. So this would equal to 1, and it's really, really simple to do on this kind of paper thing because you just drop the numbers down and you apply this AND to every single thing. So imagine the AND is between each of these numbers. 0 and 0 produces 0. 0 and 1 still produces 0. Apply the same thing to these two. Bitwise OR, you apply the same thing. Imagine there's OR between every single bit right here. And 0, imagine the zeros are false and the ones are true. So 0 and 0 or 0 still produces 0. 0 or 1 produces a 1. 0 or 0 produces 0. And false or true still produces true, which would be a 1 here. XOR, it's slightly more complicated, I guess. It's really simple. Hopefully I explain it pretty well, because that's really what it comes down to. If you don't get it the first time, just look around until you can find some kind of tutorial that explains it properly, because it's a really simple concept. So basically it's, let's say that you have true XOR false. This one would return true because you only have one true. So this one would equal true. If you happen to have the otherwise, if these were both true, basically when these two are opposite, then it returns true. If they're the exact same, then it will return false. So this returns false. If both of these were false, it would still return false. It's just if one, so here's a 0, here's a 1. XOR that, it returns a true. And you can just look at this little table right here. So 0 XOR 0, they're the same thing, so it returns false. 0 XOR 1, there's only one of either, there's one false and one true, so it returns true. And if there was only one false and one true, or one true and one false, they're the same concept, it's just flipped, and hopefully I explained that pretty well. We'll go over it a little bit more in the code review, I guess, but for the most part, hopefully this at least got you a good introduction to it. It's really, really simple. Just find a good tutorial that explains it well. Here is not, so it's the exact same concept as the other not. So not becomes, or false becomes true, true becomes false. So 0 not, actually I don't even need these, I don't think. So yeah, alright, so 1 0 1 0. So we remove this whole list right here. 1 0. And so we apply not to every single one. We're just flipping the bits. So 0 or false turns into 1 or true. 1 becomes 0, 0 becomes 1, 1 becomes 0. So that's all you gotta do right there. Really, really simple. Don't let the fact that you're operating on a bit level make it too intimidating, because it's really not that complicated. It can be once you're actually starting to really work with it, but if you can get the concept down, you can usually break it down enough to the point where you can at least make sense of enough to wrap your head around it. So anyways, bitwise continued, 0 left shift, signed right shift. So the 0 for the left shift will shift left by pushing zeros in from the right and let the leftmost bits fall off. So an example for that would be if I start with this as my number and I left shift 2, then my result would be I start off with 2 and then whatever is left over after everything falls off the edge. So you started with 2 and I would end up with 0 1, because these two numbers would be here. I would add 2 and I would drop 2, and that would be the result. So pretty simple there. Signed right shift, shift right by pushing copies of the leftmost bit in from the left and letting the rightmost bits fall off. So almost the exact same concept, except rather than pushing in zeros from the right, you're taking whatever number you started on and pushing that in from the left. So this would be, since there's a 1 on the very left, that would be what your filler character would be. So let's say go like that, and then so you add 2 1s, and then you just start with whatever else you already had. So you're just adding 2 1s here, and these 2 would fall off, so you would end up with that. And that would be your number right there. This wasn't really going to be a binary tutorial, but just a really quick summary right here. Let's just start off like that. So the way that it goes is you're going to have the ones place. Alright. You have the ones place, you have the 2 place, you have the 4 place, and you have the 8 place. And then you can go up to as many bits as you want, but here's simple enough where you can just do it all in your head. In case you're happening to do it in hexadecimal format, this would be equal with F if all of these were set on. So basically, it's just like decimal, whereas if I have 109, I'm adding the ones place, the tens place, and the hundreds place. So the 100 place, there's 1 100, 0 tens, and 9 ones. So that equals 109. The same thing with binary, where if I happen to have 101, then this point is on, so I add this value up here. So I have 1, this one's off, so I'd skip that. This one's on, so I add 1 here, and this one is off, so I don't add that here. So all we do here is 1 plus 4 equals 5. So this one equals 5. If I had a slightly bigger number here, let's say I have an 8 added in, then 13, so would be 13, which in hex would be equal to, here, you would have 10 would be an A because you start at 0 when you're counting, kind of like, because here's a 0 and then there's a 1. So by the time that you reach the number 10, you're already past single digits. So because the 0 is taken ahead of time. So you got A, B, C, D, E, F. So A would be count for 10, B is 11, C is 13, which is what we would have right here. D would be 14, 13, C is going to be 12. So D would be 13, E is going to be 14, and F is going to be 15. And then if we add another F, that would be if we had 8 bits, so that would come out to 255 or 256, I think 255 because you have the 0. Alright, so anyways, this wasn't going to be a tutorial on hex. So anyways, hopefully I explained that concept pretty well. If not, go ahead and rewatch it. Go check out some other sources. Maybe they can explain it a little bit more. Moving on. Comparison, we already pretty much went over these. Equal, not equal, greater than, less, greater than or equal to, less than or equal to. This is all stuff that we've known since elementary school, so there should be no problems there. Identity. Is, not are going to be your 2 options for that. So is returns true if both variables are the same object. So for instance, a bird is bird would return true. Is not returns true if both variables are not the same object. So bird is nest is not nest would also return true because a bird is obviously not a nest, and certainly not if we're talking about the same object requiring the same memory location. Which brings us to the next point. Identity operators are used to compare not if objects share the same value, such as x and y both having the value of 10, but if they are actually the same object with the same memory location. So for instance, if something was stored at hex value AF, BC, whatever they would have to have the exact same memory. So X would have some random memory value. Let's say it would have the value of FFDC, right? And normally it would probably be 8 bits or more, but just off the top of my head, here's what we got. So this little \x just indicates that you're dealing with hex numbers. So yeah, there's that. So all you're doing is if x is equal to this value right here. So you pretty much have to have the exact same object for them to refer to the exact same memory object. So logical and or not. Similar to what we just covered with bitwise, just slightly different what you're working with, units of data. So for and, returns true if both statements are true, or returns true if one of the statements is true. And not reverses the result, returns true if the statement evaluates to false, and vice versa. So if, hopefully this makes sense, because we already covered it as well. But if you want, go ahead and reread this and then go back to the bitwise section and see if that'll help make, if you still haven't gotten it. But it's a really simple concept, maybe just to give it a few tries and you got it. Alright, so membership. In or not in In returns true if a sequence with the specified value is present in the object. So for instance, car in car collection list or array, if you happen to have experience with that. If not, a future tutorial is covering lists and or arrays. The same thing, just different name, depending on what language you're dealing with. Not in returns true if a sequence with the specified value is not present in the object. So bird is not in colors list would return true because a bird would probably not be in a list of colors. Notes. Operators with mixed type operands convert integer operands to floats. So if I were to add, for instance, 10 plus 1.1, then the whole result would turn into a float. So it would be 11.1. So, and the same thing if you have like 20 integers and one float. If there's a single float, you're going to still end up with a float afterwards. In interactive mode with idle interpreter, the last printed expression is assigned to the variable underscore, allowing for easier continuation of calculations when using the interpreter as a calculator. So this doesn't quite fit in with this lesson, but for some reason I added it earlier in the notes. So it's just a good little tidbit to know, just in case you haven't any. Don't explicitly assign a value to underscore, as it would just create an independent local variable and mask the behaviors of the built-in underscore. And moving on to the code example, pretty much I just made not really a table, but I just listed it out as simply as I could. So as standard, slow enough that you can pause it if you need to. Alright, and just in case you want to, here's what the results are going to be. So really simple stuff. So basically I just took every single operator group and just showed what all the results would be. So for arithmetic, 10 plus 10 equals 10 plus 10. 10 minus 10 equals 10 minus 10, and the results are right over here. So 10 plus 10 equals 20, 10 minus 10 equals 0, 10 times 10 equals 100, so on and so forth. 10 exponent 10 would be whatever that number is. And then for the assignment, all of these, since I already covered the concepts earlier, I really didn't feel like writing out every single example because, yeah. But basically what you do is, so here's x, get 0, x plus and equal to 20, and so your result is going to be whatever starting at 0, so 0 plus and equal to 20. This right here would be the exact same thing as if I just wrote x is equal to x plus 20. So I can go ahead and comment this part out, and then if I refresh it, where are we at here? X plus, alright, so for right here, this result should still be 20. So clear that out, go there, and then for the operator, for the assignment, still 20. So that should check out. For the bitwise thing, admittedly, there's a little bit more research I have to do into this particular topic. Even if I get the concepts, the actual code and all that. So I'll walk you through with what I have right here. So here's the bitwise AND or XOR not left shift right shift. So I assigned 10 to X. Well, here's where my problem came in, was that I don't know the exact binary representation of each of these values. So just because this is 10 doesn't necessarily mean, alright, so 8, 4, 2, 1, right? So just because I have 10 doesn't mean that I'm dealing with this number right here, right? Because it depends on whatever the engineers and the programmers decided to assign this particular value to, at least to my understanding at this point in time. So like a could be a totally random number, and so it's the same thing. So 10 is just a different symbol than A or B or whatever else. So there's probably actually some kind of way that you can just print out the bit values, but I don't have that off the top of my head. So anyways, here, just so you have some idea, so bitwise X, or assign 10 to X, Y to this, and then I left shifted the bits, and then somehow, I'm pretty sure, the resulting value would be this. But I don't know what this equates to in hex or binary, so that's where I'm at with that. But hopefully that gives some kind of insight into how exactly all that stuff works, especially factoring in the slides that we went over earlier. Again, really, really simple concepts. You're just dealing with ones and zeros and flipping it or whatnot. It's just, there's a lot of other implementations when you actually get to the level where you're actually programming it legitimately in the real world. moving on for comparisons. A is B. That one has no need to be there. Oh, right, this one's just showing that we assigned it. So A gets 1, B gets 2, as we showed up here. And then we compared, is it equal to, is it not equal to, is it greater than or equal to, less than or equal to, and all of these results you can see are right here. So as for identity, these ones get a little bit more unique compared to what we learned all of grade school, but they're still really simple concepts. So for identity, it's I gets the number 10, J gets the number 20, print I is I should return true because they're the exact same value, so they have the exact same, this variable is going to have the exact same memory address as itself. I is not J is also going to return true because obviously the memory location of this object would be different from this. And I'm pretty sure pretty much everything's an object in Python, though don't quote me on that part. So for logical and or not, print true and false would return false because all of these has to be true if you're dealing with and. True or false is going to be true if there's a single true anywhere in that. So even if this went or false, you could have a million falses and one true, and as long as you have or for all of them, they would still evaluate true. And not true would obviously become false because it's that same concept as bit flipping, where it would just become true becomes false and vice versa. So as for membership, this one's going to deal with sequences, so things like strings and arrays, lists. So A in animal, this one's going to become true because this character right here appears somewhere in here. And then A not an animal is going to return false because obviously this one appears right here. So hopefully all of that makes sense. You can read over all these again. There's that, and there you go. So just in case you wanted to check over any of those. So that's it for this lesson, and